Hi, my name is Amy Sullivan, and I am the current Vice President of AAAR, and it's my pleasure to welcome you to the 31st in our monthly AS&T lecture series. This is a new initiative being supported by the Freelander Memorial Fund. So with these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities, and also give us an opportunity to come together outside of the annual conference. So each month, the editors of AS&T select a high-impact paper to be presented by its authors. These lectures are being recorded and will be posted to AAAR's YouTube channel, which you can access from our webpage under the Events tab. In addition, each of these lectures is being hosted by one of our student chapters. So I want to thank everyone who's helped to make these lectures happen, and also all of you for joining us. And with that, I'll turn it over to our student chapter host from Clarkson University. Thanks.
Hello everyone. Welcome to another exciting lecture in the AAAR lecture series. I'm Naga, the current student chapter president of AAAR here at Clarkson University. And it's my great pleasure and honor to introduce today's distinguished speaker, Professor Pratim Biswas. Professor Biswas currently serves as the Dean of the College of Engineering and is a faculty member in the Department of Chemical, Environmental, and Material Science Engineering at the University of Miami. He received his PhD from Caltech, his master's from UCLA, and his BTech from IIT Bombay. To touch on just a few of his many achievements, Professor Biswas has mentored and graduated over 65 PhD students and has published more than 475 journal articles. Among his numerous accolades, he is the recipient of the prestigious Fuchs Memorial Award by AAAR, recognizing his outstanding contribution to aerosol science and technology. Today, Professor Biswas will be presenting on an exciting topic, AI and ML methodologies to solve the Aerosol Dynamic Equation, the coagulation terms. The lecture will have the usual format with around 45 minutes of presentation, followed by time for questions and discussion. So at the end, please feel free to unmute yourself, raise your hand, and meanwhile, please type your questions in the chat box. And welcome, Professor Biswas. The virtual floor is yours.
Okay, thank you, Nagarajan. Thank you, Amy. This is a fabulous series. I'll encourage all of you to, I presume it's done monthly, to tune in and listen. And today I'll, of course, be presenting the work of one of my PhD students. Always thank our students first before we run out of time. Onochi Okonwo. He is the first author of this paper. I just get the pleasure of presenting it. I hope he's listening in too, so he can tell me how well I did with respect to presenting his work. Other students have all kept me going over the years, and of course, I have to acknowledge several of the funding agencies. So it's truly a pleasure and honor to present to you. I thought I'll start with, very briefly, I'm supposed to talk about the paper, but we always think about, technological innovations, and this, of course, predates even some of us who've been around for some time. If I just put buckets, and these are just random in some sense, you'll find different things. There was a quantum age, maybe early 1900s. And in brackets, I say what it has resulted in, maybe nuclear power, nuclear energy, but more importantly, going below a small particle to the constituents, and even below that, and, talking of quantum things. And today you hear about quantum computing, all kinds of things. So in some sense, it continues. It, of course, might overlap, if I mention quantum computing, with the information age, which started with the digital or caused the digital revolution. And we are all familiar with it. In fact, today's topic, I'll talk about machine learning in a very elementary way, but it's really a fascinating field with respect to all the applications and even fundamental developments. And then the biotech age, genetics, health, human health. The thing I wanted to point out, aerosol science and technology really has some connection to all of these ages, right? If I pick the biotech age, we just overcame a pandemic, maybe went into it because of a lack of understanding of airborne transport of small particles, viruses in this case, but human health continues to be a significant aspect of importance. So, and I just write down some of these things. So the quantum age, molecules, clusters, diffusion, even Einstein's work, early 1900s, and today's topic, coagulation, that I'll refer to the Polish scientist that I'll come to. The information age, allowing us to solve complex mathematical models describing aerosol phenomena. So here maybe as a tool, and as I said, that's the topic today. And then of course, health effects of particles, pharmaceuticals, and all kinds of things. So I thought I'll just mention that. Artificial intelligence, I don't like that term. I like augmented intelligence. There's all kinds of discussions going on. Is human intelligence going to disappear? What's going to happen? Are jobs going to disappear? But a very fascinating area. Then I picked this from a professor of Stanford who makes a beautiful presentation, Dr. Fei-Fei Li. Please listen to her TED Talks. They're just fabulous. So, you want to really have a artificial entity which begins to think like a human or has the capabilities of a human brain. It probably never will to be even, at least that's my personal thing, but it can be a big assistance. And that's why I like the term augmented. And you deal with large data sets and it's just fascinating, even our own neural systems, we handle big data, we interpret very rapidly and so forth. So it's done through a network of neurons, but here you have artificial neural networks which run on graphical processing units. A big driver in this is, seeing, which means I want to visualize the data, I want to understand it, and then I want to do something about it. And that is the broad field of AI and so forth, and truly fascinating. And her talk is really, I would recommend every student to go find her on the internet and listen to her talk. Today, I'll just be dealing with numbers, very limited way. We are not, computer scientists here, but more application folks, and I'll of course apply it to aerosol problems, dynamic problems, and solving it. So in essence, we take a complex understanding and it's data again, and the data can come from experiments. So I'll show you later some selected papers. I'll just list the papers. They are very much data-based interpretation. So satellites give us a lot of data on aerosols. How do you take that? How do you relate it to the climate and so forth? So a lot of papers coming out in that domain. I'll be just picking a simple thing and trying to solve aerosol dynamic equation. And even in that, just a single term, right? So you basically take a complex equation and you convert it to a series of layers and convert it to maybe a matrix multiplication type of problem. So on the left, we have inputs. I want a certain set of outputs. I might have multiple layers of matrices. I do the multiplication and I get the result. So you can see this equation here. The output at any layer or the value at any layer is just given by the previous layer value and multiplied by a weight. Each of these might have a certain weight influencing this number. And then, of course, there is a bias term. And the bias term might be related to the physics of the problem and so forth. And of course, you want to minimize the error and so forth and come up with a simplistic model. So that, in essence, is the level to which I will get in. So let's pick up. If I look at the problem, we start with molecules. The molecules end up with a certain distribution. We call it the size distribution function. I need to know the number concentration, N, of a certain size. And we often use volume as a metric of size. You could use diameter, but because of the shape, the volume is more readily defined. There's another reason related to coagulation, which I'll refer to. I'll throughout the talk just use volume as a metric of size. And if it's a nice spherical particle, many times we assume that there is a clear relationship. Okay, so we can do a number balance of this entire process. I'm interested in the change in the size distribution function because that is what physically characterizes my aerosol. And there are many applications, whether I'm using it to, let's say, if I happen to inhale this, what fraction might deposit in my respiratory tract, or if I want to make a thin film, if I want to make a catalyst, the properties would depend on this, right? Or if I just want to make a powder, I need to know the size distribution. So the change of that is important. Things move about. It could be a reactor, it could be transport in a room, it could be outside in the atmosphere. So the first term will just give me the transport terms. I'll show you later. There's a bunch of modalities of transport. And then the size distribution will change. These are coagulation terms. I'm going to come to it later, so won't go there. The particles could grow, which means molecules could associate with the particles, and with that, the size will increase. And even the first step itself, I might start with molecules, but end up with a cluster, which I define to be my aerosol or a particle, and that's a nucleation term. So even by looking at this, this is not a mathematically simple form of an equation that I can readily solve. And then if I start adding the transport terms, this velocity term in non-dimensional form is impacted by the fluid. It might be moving, the inertia terms, the diffusion terms, gravity-based terms, thermophoresis, and I can add even more mechanistic transport modalities, right? So this really becomes complex to solve, right? So I just want that understanding if I want to solve this full thing. And then within the particles, I might have mechanisms like sintering, the shape might be changing. They happen at different scales, like nucleation is at the molecular scale all the way to, very large scales. So that's another thing, that volume, the size metric goes over several orders of magnitude, which again adds to the complexity in solving it. So let's now just look at the coagulation term. I know this might be simple for some of you, but maybe it's a little tutorial mode too. So I'll tell you what collisional growth is, or in this sense, coagulation. So I have two particles. For coagulation, I need to have an aerosol. It's not the formation of particles, not the birth. So I already have an aerosol. As I said, I'll refer to the size as Vi and V sub j, and they can be anything, any number, which of course relates to reality and the particle size that exists in the system. Because they're moving around, these two particles might come together or collide together. And if conditions are right, maybe they stick together. And we use the term coagulation to say that it becomes a nice spherical particle. Some of it is to keep things simple, but they don't need to be. And I will form all kinds of agglomerates and so forth. And that adds to the mathematical complexity. Today, I'm just going to use machine learning to try to even solve this equation and show you. And of course, then I want to use these techniques for that full-blown equation that I just described. Another thing to note is if I use volume as a metric, I think I mentioned it, when they both collide and become a single particle, the new volume or the volume of the resultant particle is just the summation of the volumes, right? Of course, there might be certain complexities happening, but let's just say it's a simple additive process. The other thing to note is initially I had two particles, now I have one. So the number concentration decreases. And some of these simple rules are very important. And this also tells you about a mass balance kind of consideration that I have to make sure in coagulation it's being satisfied. Okay, so now I take this. We of course lean on certain individuals. Here's a picture of a Polish scientist. I think he was from Poland. Yes, Smolechowski. who of course hung around at I think overlapped with Einstein and so forth. Einstein was looking at the diffusion of particles and coming up with elegant expressions, and that's what probably resulted in particles colliding. And Smoluchowski then came up with a very simple but elegant description. So I'm interested in how the number concentration of that K-size particle changes. As I said, I and J will collide to form the K-size particles. There is a double counting that takes place. So that's why we have that term half. And beta is a collision coefficient. It depends on the size of the particles. If it is uh, Brownian diffusion, we know the expressions. I can use it, derive expressions for beta, or it could be any other mechanisms. But interestingly, there's another loss term because a K-size particle is also colliding with everything else, right? You see I going from 1 to infinity. So when I collides with K, that's a loss of a K-size particle, so this negative term, and I have to really account for it in the number balance equation. I can then do another summation over all K-size particles and find out the total number concentration change, and this just adds to the complexity in the mathematics. And if I write this in continuous form, which I really want to do because I want to use elegant mathematical techniques or even numerical techniques, I end up with integrals. It's a integral differential equation. Here in continuous form, a particle of size v collides with v minus v hat, and then of course I sum it up to get all the new size particles, and similarly there's a loss term, right? So this is the equation I'll be playing with today. There are certain time constants. Whenever we look at complex problems, I try to come up with characteristic time expressions. Of course, even in the numerical solutions, by non-dimensionalizing, I can use certain parameters. I'm not going to derive this. There are two regions, the continuum region at the bottom, which gives me a simpler form of the characteristic time, and then the free molecular region, which means the Knudsen number comes into play, and so forth. And I will use this as a time increment, and I'll come to this later on, but I thought that approaches like this are also important. We can do order of magnitude analysis when we are solving these complex equations, right? So let's keep going now. So the general dynamic equation, again being put out in full form, and this should be a v hat here. But anyway, v colliding with v hat and v hat colliding with v minus v hat. So we get the number balance. I'm repeating that equation. There are different modeling approaches. I can assume all particles remain monodisperse, which means at any time instant, of course, it's a forced assumption that all particles are all of the same size, in which case this sort of equation, or I'll just call it complex looking equation, can be simplified and readily solved by a simple integration, even closed form integration. I can go a step beyond and have a modal description. I don't assume everything to be the same size, but I use modes. There are stochastic techniques, which means I might put a bunch of particles in a box and do a computer experiment by moving them around, and then seeing when they collide and touch each other, how the distribution changes. So this is more a computer experiment. Log normal, I assume a certain shape. Discrete is the most accurate. I'll talk a little more about it. Sectional, that our community uses extensively, and then a combination of discrete and sectional, which we could also use. And there might be other approaches. I just listed a few of them here. And just continuing, let's just say I'm going to use discrete. What do I mean by discrete? I'm really accounting for every possible size, right? I start with a certain minimum size, maybe in my distribution, and then every size I'm accounting for. So here is a simple example, and the same thing could be applied to nucleation too, which means I have to start dealing with the molecular size, and I've just picked a number, zero point 0.1 nanometer. But let's say my first particle or smallest particle is 1 nanometer. Remember, I like to use this volume term, especially for coagulation. I've just used a spherical assumption, and pi by 6 dp cube gives me that volume in nanometer cube. And then let me just go up to 100 nanometers just to illustrate to you. Of course, we deal with submicrometer size particles, even micrometer size particles, and I should really take it even further. But let's just stop at 100 nanometers. And then you can see if I'm accounting for every possible size, which means 1 nanometer or this volume, the next size will be double this volume, 2 particles coming together, 3 particles, 4 particles, and so forth. And I can find the number of discrete sizes. Here I've used the volume of a molecule just because if I want to consider nucleation, or you could take the volume of the smallest size, which will give you a fewer number of equations, but still humongous number. And if I want to solve for the concentration for each of these sizes, just imagine I have to solve, close to 1 trillion equations or 1 billion equations. Definitely 1 million+ equations, right? Even in the small size range. So that makes it really difficult. While it would be the most accurate representation, even computers, we would run out of horsepower. Another approach is to assume a certain shape for the distribution or use these method of moments. And I then transform the coagulation equation to a moment equation, a kth moment, using the definition of moments, which means I just integrate by multiplying by size raised to k, and I get a series of moment equations. Okay, so these are all approaches that can be used, but I hope you get the picture that the horsepower, the computing horsepower required is significant. And I'm just talking about coagulation here. And one can summarize this looking at all these different models I talked about, and you can read these. I guess there will be a recording, or if anyone wants the slides, just send me an email. I'll be happy to send you a PDF. Some of this is in the paper also in Aerosol Science and Technology. So just summarizing again, discrete model computational cost is very high, but the accuracy is high too. And I bunch a series of those models. I want to reduce computational costs, so I can look at complex systems, but then the accuracy also begins to drop and so forth. It's very clear we want high accuracy, low computational cost. And this is where the topic for today, which is hybrid machine learning models, will come in. And that's what I'm going to present to you, which is the subject of the paper. Okay, so a lot of people are doing this. I'll point Nicole Reamer's paper, which also motivated us to look at this. And she uses combinatorial neural networks and then applies it to natural systems, atmospheric systems. But as I said, a lot of satellite-based researchers who look at aerosols and climate forcing use these approaches and so forth, right? And these are not all of them. This is increasing by the day and more. Our approach is to see, can I use it for practical systems, engineered systems, where I'm interested in solving the aerosol dynamic equation. In this case, just looking at the coagulation term as a first step for illustration. Okay, so this is the algorithm, and it is simple machine learning. The first thing, I need a data set. I could go into the lab and collect data, but I'm an experimentalist primarily. But if I tell my PhD student, you need to do 60,000 experiments, they're going to, of course, panic, and they'll be here forever. So we do this we use the most accurate sectional model with a very fine section spacing. And some of this is described again in detail in the paper. So I start with an initial size distribution. I really convert it into a log normal model just to get parameters. And that's again a first step. You don't really need to do it, but to reduce the number of factors, solve it for different time intervals, which is a function of this characteristic time. And I just list a few here, and I get a distribution. I fit a log normal. I'm assuming I'm going to keep things log normal, and I get three parameters. A log normal distribution is described by the total concentration, a geometric size, and a geometric standard deviation, or three moments of the distribution, right? Uh, Onochi ran this for 60,000 times. Even that takes time, but he then has a robust data set. This is not what I want to do because even running this takes a lot of time. It's quite accurate, but this is my baseline, which gives me an input parameter, a time, and a final set of size distribution parameters. Okay, then I do a training process. So in any machine learning algorithm, you need a data set, and then you need to train using this data set. So my goal is to use certain input parameters, and eventually I want to use it in a reactor, in my case, or you might want to do it in the atmosphere or in any other system where you want to solve the aerosol dynamic equation or the general dynamic equation. So the time is important because that I want to run it for so much time. I need the initial parameters of the distribution, and the physics will be impacted by, for example, Newton number, which tells me which regime I'm in. I use this data set to, we call it training, which means this matrix approach. These are the hidden layers, which takes these input parameters and relates it to the output parameters. And there is nowadays, you also get, even in a program like MATLAB, a full-blown MATLAB package, you will get artificial neural network models, even different types. There are in this case, it's the Adam optimizer algorithm. You minimize the mean square error, which relates the input to the output. Okay, so this is a conventional, simple machine learning problem. Again, a data set, training, given an input, have a matrix multiplier, I'll get the output. And here, remember, I'm using it to train it, right? So I'm coming up with this matrix form. I'm coming up with this simple algorithm which relates input to the output, or relates the output to the input, right? I, of course, have to validate it. So I would then choose another 6,000 sets, in this case, 6,200 sets, and run this. So I take an initial size distribution. I do this. I do split up the time because the time can vary, right? It's a parameter. It could vary. But I use an iterative algorithm to improve the accuracy using the characteristic time as a sort of step size. But my final time might be 10 times the characteristic time because I want to run it, or it might be a fraction of the characteristic time. If it is much larger, I just reiterate this process and I come up with the final particle size distribution. So in essence, this is the overall model, right? In some sense, simple. Of course, there's behind the scenes optimization, minimization of error, and so forth. I need to check how good this is. So I said I trained with 60,000, and then I ran it for 6,000 different initial values. I do run the sectional model, so I have the accurate thing, but I've used the machine learning model to give me this output. Again, the total number concentration, the geometric mean size, standard deviation, and then also tracking the total mass, the total volume, right, which is representative of the total mass. And you see that the error, this is a relative error, which means it's a difference between the accurate value from the sectional model and my machine learning model, and normalized with the accurate number. And you see that as the time increases or number of iterations increase, the error goes on. There's a lot of variability also, right? Because I repeat the calculations and I get that. So if I were to summarize this, you see that it's a conventional ANN model. There is a mass conservation error. And then why should I have 13 iterations? What if I had 1,000 iterations to do because of the time scale? Then I'm going to have significant error, right? So there are, remember that term, the bias term, I can force a aerosol mass conservation term because I know from the physics mass has to be conserved, and our colleagues at IIT Bombay who were co-authors in this paper have actually demonstrated that very nicely. And I think Nicole's students have also used something like this. But our approach is, let's propose a hybrid ANN model where I try to bring in the physics into it. And that really is the subject of this paper, not just rely on a conventional model, but do a hybrid model. So in this case, again, I will have a sort of conventional machine learning model, but I'll force in a reduced order GDE, and this knowledge comes from the physics. And in this simple case, I can do that, but I can use it as a modular tool to increase the accuracy, maybe reduce the time further, and then start combining into a very large complex model, right? And today I'll just be demonstrating this kind of an approach to solve these equations. There are advantages. It reduces the complexity. Physical laws are always good. We love our physics. We don't want to violate that. In this case, aerosol physics, it's computationally also more efficient. The resolution depends on this reduced order, because I still don't want a full-blown physics model, because then the time will keep increasing. And if I have a full-blown mathematical model that I'm solving, that is just going back to what we already have. So I want the resolution depends on it, and then I can apply it to different systems, which ultimately is our goal, right? So here, let's look at it. So the steps, it pretty much follows what I described. But the first step, we love non-dimensionalization. So I take all these coefficients, the equations, I non-dimensionalize it so I can begin to bound them. I can track the physics well, and it's very straightforward in some case. And some of this is already there in the literature, but I end up with a non-dimensional coagulation coefficient, and I will be imposing the physics via moment model. And that's why I have three moment equations. The second moment equation, which is the total volume that's conserved. So I have two additional forms of the coagulation coefficient for the different moments which I have to use. Again, there are some details in this I'm sort of glancing over, but the first thing is just coming up with some non-dimensional parameters, right? And then repeat this equation here in moment form, U and V colliding together, and in the moment form integrating with that V raised to K, I get an equation which looks something like this. And then I'm going to say that I'll choose a time step where I force this collision kernel, these beta values, to be a constant. If the time step is short enough, I can do that. And if that is so, I can pull this out of the integral and end up with an equation like this. Now, for example, if k is equal to 0, this is a very straightforward term. It's minus half beta k star and then this m0 squared, because integrating each of these just gives me the total number concentration. So I end up with the three moment equations in non-dimensional form in very straightforward form, right? And the second one, as I said, the volume is conserved in a coagulation process. So this is just equal to 0, and you can set k equal to 1, and this will come out to be 0. And of course, k equal to 2. And in non-dimensional form, I have this. So that's the first step that I do all of this. I take this, and in some essence, if for this constant value of beta naught star, I can just integrate this out. Remember, this is a forced assumption, so this would only be true for a short time interval, correct? We have to keep that in mind. And then this is how I generate my data set. Again, initial distribution, get a final form, fit it, but then also get expressions for beta naught star and beta 2 star in terms of these moments, right? That basically comes from this solution. Again, remembering that these are constant values and forced to be constant. And at the bottom, I just tell you how many times we run it and so forth. The next thing is to get the training done. Right now, the training is done in that same old-fashioned conventional way. I want a bunch of weights. I want a bunch of layers. I want a bunch of bias factors. I again want to optimize it so that the error is minimized, and I come up with these matrix. So given an input, I use matrix multiplication to come up with values of beta naught star and beta 2 star. Okay, and this is where I put it together. So the only difference is I'm forcing a sort of solution based on the moments for a short time interval. So I clearly have to do this iteration time and time again, and running it for one characteristic time interval allows me to have a reasonable assumption and then get a final particle size distribution, right? So you start with the initial, I have this model, the matrix multiplier, I get the values, I haven't reached my final time, so I use these new set of values to redo this and just run this thing again and again. I have to again then check this out, but in this case, I picked another graph from the paper where I show you a dimensionless size distribution function plotted with size in this case. Of course, we run in terms of volumes, as I told you, but this is just an illustration for different time intervals. And the solid line is the sectional model done painfully and to ensure that this is pretty accurate for coagulation with good mass balance. And you see the dotted lines are the ANN model. Yeah, there is some deviation, right? And so forth. And that's what we want to track. We want to minimize that deviation. But you see that the ANN model definitely works better than the moment model by itself and would be a better approach, though I have incorporated over a short time interval the moment model. So there are all kinds of error terms which people report. This is a lot of statistics, a mean square error, a mean absolute percentage error, and the mean absolute error. It's just different statistical quantities. You can compare the hybrid to the moment, and the baseline or the most accurate in this case is the sectional model. Now remember, the sectional model is the one that produces the data set, right, for us to compare. And this is, of course, a computer experiment we are doing, but in reality, I could have a physical reactor, I could have instrument-based data, and I could use part of that data to train to get the reactor performance and so forth. So you see that, of course, the hybrid artificial neural network model tends to be more accurate than a moment model, and it seems to work well. And of course, one has to put it together in the detailed thing. So this is, there are applications. Ultimately, we are application driven. And I show at the bottom a titania industrial reactor. By the way, these are powders that are produced in millions of tons per year. You'll be surprised if you don't have some titanium dioxide on you, either through your sunblock. In Florida, we need that all the time, or in some kind of photocatalyst, or in some kind of cosmetics. Silica is the same. If you like a crispy cookie, you are actually consuming nanosilica particles in low concentrations. Carbon black, if not anything, some of you will drive your car back home. The tires are still made with carbon black to strengthen the rubber that is used in tires. So these are produced in tons per year and all by gas phase processes, or I would love to call them aerosol processes because that's what they are. And this is, of course, taken from a detailed modeling study by a European group. And I took this picture from them. So they sort of give you this entire process. You walk into our lab, you'll see reactors like this. This is a furnace aerosol reactor. a flame aerosol reactor, and we produce particles for all kinds of applications, or even to study atmospheric systems or degrade some naturally problematic particles, or understanding fuel combustion, which produces particles. This flame looks whitish because it's titanium dioxide that is being produced. So I could even get data from these systems and be completely data driven. And if I go to folks industry that makes this, the first one was DuPont, which made TiO2 by the aerosol process, which made them very commercially successful because it's a fabulous technique to produce it. All the competitors were laid to rest. This was done 75 years ago, and they had engineers who just understood this by observation and measurements, right? And who could describe what would go wrong. And here, having better mathematical approaches would be good. So I look at the number concentration, all the usual parameters of the size distribution function, and I compare it to the sectional model and the moment model, and you see we get very good agreement, or reasonable agreement, enough to use these models for even describing these systems, right? And of course, the goal is to produce a certain size at the outlet and certain standard deviation, and you can then begin to design these reactors to operate that way. So in a very quick nutshell, I'm running out of time. I should bring up computational cost even in a simple way. We compare the CPU time. So clearly the sectional model takes a lot more time, and the longer the simulation time, non-dimensional time here that I plot, the more computationally expensive it is, right? And obviously if I start throwing in additional terms, so this is just a simple way of looking at the coagulation solution terms. The hybrid ANN model is pretty flat. We expect that because once the training is done, I'm pretty much set, right? The time could increase significantly, but it's a matrix multiplication, which the computers, the GPU systems are easy. Log normal increases slightly, and you see log normal model, because of its simplicity, is more inexpensive than even the hybrid ANN model, and one would expect that, but the accuracy is also compromised. So, you make that decision, but this is the kind of analysis that you could do. So with that, I'll pause. I hope I gave you a simple description. If it's too simple, please excuse me, but do read the paper. There are many details, and ultimately, if there is an interest in using these things in your own studies, please explore them, and allows you to do a lot of computations in a more effective manner, and developing tools which then the community can use. We strongly believe in sharing. If you want to run these things, have a simple system with only coagulation, feel free to download it and run it, or tweak with it. I think the source code has to be posted too, so you have access to it. And I think a message to the community is maybe AAAR. I know Amy is on or was online, is for AAAR to set up these libraries, right? We used to have them, but now the systems are a lot more prevalent, but really creating libraries which our students and other researchers have access to, and so forth, like the sectional models, the discrete sectional models, maybe later complex climate models, but categorizing them. But for us, our lab has a GitHub site. Feel free to download it. With that, I have to thank the students again. And thank you for listening. It's really a fascinating field. You all are all committed aerosol scientists, mostly, I presume. There's a lot of exciting things happening. If you visit here, we do a short course. We call it summer school in winter. When you're freezing up north, come down here, and we'll guarantee that all you'll need is a t-shirt, but you could also listen to some wonderful presentations, or if you're just visiting here, swing by and visit us. There's a whole bunch of aerosol researchers here. With that, I'll pause. Thank you for listening. I'm happy to answer any questions. I don't know how I should see the chat box. Naga, if you could help me read out the question, I'd appreciate it. Okay, thank you.
Yeah.
Or anyone can unmute and ask, right?
Yeah, definitely.
Trying to. Presume there are no questions, right? Or there's one in chat.
Yep.
Yes, I mentioned this, right? So one could add that the loss function, you could add a forced mass balance or a mass conservation expression to that, and you could do that. We haven't used that approach in ours. We wanted to come up with an iterative scheme which was more built in with some kind of forced physics. In this case, just for simplicity, we use the moment form of the expression, right? So there are many ways to do it. I'm not very familiar with PINN. If it is a sort of standard algorithm, we look it up and see, but we developed an iterative technique to use with our own physics-based information being incorporated. But the loss function approach is used also as by many. I refer to our collaborators. Professor Goody, his group has been doing that for multiple problems. So it's not just aerosol-related problems, other transport equations and so forth that they solve. Yeah. Reaction engineering systems. Good. Any other questions? Feel free to ask. Right. The input. Yeah. Another question is, how do you choose the input parameters? Of course, as I said, for the conventional model, which is a brute force black box type approach, we used a lot, as you can see, 60,000 distributions. We tried to relate to our physical systems in the lab, where we do a lot of synthesis work and study these systems either for carbon quantum dot production, catalyst production, like composite oxides, or other species, right? Or destroying PFAS in soil, for example, something that we are doing now, or using waste lignin from biomass systems, paper production systems to make value-added systems. So we relied on that. So in some sense, it's arbitrary, but we covered typical size distributions that we experience in our high temperature reactors. Okay, so nothing specific, if or no guidance but I would say relating it to your system of interest is important.
Any more questions? Wait for a minute or two.
Okay. So it's mainly students attending. I see Vladek is listening. Thank you, Vladek, for joining. So I recognize some names at least. Yeah, most of you seem to be students. So I hope all of you are preparing to come to AAAR conference. Fabulous meeting.
We do have a question from Mike.
Oh, sorry.
Have similar approach been applied to larger particles and gravitational kernels?
No, we focused on more the smaller particles, nanoparticle regime. Again, that's because of the immediate interest, but you could definitely apply it to larger particles. In that case, maybe transport and, yeah, like you're saying, gravitational kernels. Yes, so the equation I showed you at first, you would go back to that, right, as the governing equation. Either you need to have data to solve it. So in this case, non-dimensionalized in terms of like a fruit number, but it comes in the transport term for the particle movement here. You could, of course, use inertia if it's larger sizes and depending on the system, and then solve this equation. Either you would need an accurate solution, which you can do by, hardcore numerical techniques. Of course, if you have access to a supercomputer, that's great. Or if you have experimental data. Uh, the models are being used in physics form to really generate the data sets. In reality, you want to look at systems where you have a large data set also available, measured by good instruments and so forth. But a combination is good. So I haven't used it we haven't used it, but others can. Yeah. Yeah, the next question I think is, yeah, Anand, I presume you're tuning in from India. If it's the same Anand, I know. Thank you for listening. I also saw Dhruv Mitru, my good old colleague from St. Louis. Thank you for joining. Coming back to your question, this is great. Why am I assuming log normal? And in some case, we kept things a little simple. It gives us a closed form solution for a constant coagulation kernel. And if for some reason the distribution is not log normal, which happens many times, especially if I have a burst of close to monodispersed particles, it takes some time to evolve into this shape. Then we would have to use more a brute force approach for the training. And also, if I wanted to incorporate the physics base. So our thought was, if the time simulation time is large enough, ultimately many of these systems come close to a log normal, so it works out pretty well. Okay. Yeah, thank you for listening. I presume it's late in India, but thank you. And good. I hope I gave you a decent answer. Yeah. Any other questions? Comments are also welcome. Yeah, like moving away from a log normal assumption is a good one, and we should give it some thought.
Okay. Um, okay. If there are any further questions, we can wrap up the session. So thank you, Professor Biswa, for this fascinating and insightful lecture. And thank you all for attending today's lecture. And I look forward to seeing you all in our next session. Actually, I'll see many of you next month in Albuquerque, New Mexico. So at the conference, thanks again, and have a great day.
Okay, thank you all. Thank you for listening.